in the L group. And in particular, I defined some L groups. For example, I said for sp2n over, say, the basic field, the L group was SO2n plus 1 C, for example. And for SO2n over the ground field, the L group was going to be SO2n C. There'll be a semi-direct product, perhaps with the Galois group here. K is some large extension of the basic field. And this semi-direct product is defined by mapping this onto a Galois group of a quadratic extension that must, of course, be contained in K, and letting this act via the usual outer automorphisms on SO2NC. What we see in these cases, and the one case I omitted, namely, well, let me put it in, SO2n plus 1 over F would be here the sp2n. What we see is that these groups are all naturally contained in GLN of C. And if we put in a Galois group, they're all, to really define the L group, we have Galois K over F, which is the Galois group, which is the L group of GLN. So functoriality, sort of the simplest cases of functoriality, are defined by these three embeddings into GLN. So one of the first problems for dealing with functoriality would be to deal with these three cases. And there actually is a project, hasn't been carried out, there's a project for dealing with functoriality in this type of situation. It was based, the original idea, to some extent due to Jacquet, although Saito and Shintani had related to ideas of Saito and Shintani for base change. And this project, I think it's fair to say, is being systematically, there are difficulties with which I'll come to, but in one person who's trying systematically to overcome these difficulties is Arthur. There are others as well, but in particular Arthur is. So the idea is to use the trace formula, about which I won't talk today, and that was also developed by Arthur. And let me tell you the kind of difficulties that, before I begin, let me just give you an idea of the kind of difficulties that are involved, and to which I'll return later in one specific example. There is endoscopy, and I'll come back to this. This was developed by Schellstadt, but in particular, in connection with endoscopy, there is one important problem to which I won't return at all today, but I want to mention it because it's basically it's the main obstacle to this program that Arthur wants to carry out, and various people are trying to deal with it. Hales and Wallace Berger has done some things. Clozel, Kotwitz. It's a really serious problem, which I won't return. All right. And what I want to do today is to discuss these ideas or the results that one can obtain in the context of the group U3 over F. This is a case where results are complete. There's a book on the subject by Rogovsky, whose title basically is something like Automorphic Forms for the group U3. Before I begin to discuss U3, let me just make a comment that these the results are obtained by using equalities between two different trace formulas. And I would say that for those of you who are familiar with the trace formula, or at least with the word, that these cases and closely related cases exhaust the possibilities for using the trace formula. Now, that puts us in front of a quandary, namely, where does one go once Arthur's program is complete? That may take a while, but one can see what's happening there, but one can also see that one day it may be terminated, and then what do you do? Nobody really knows, but the question that arises, and it's an elementary question, is whether or not one will ever be able to use inequalities. In principle, I mean, harmonic analysis should allow one to use inequalities as well as equalities. And but no one has ever really, I think, no one has found a way to do that yet. All right, so what are the advantages of U3? So now let's for the rest of the day we will discuss U3. Let me say something about the final lecture. The final lecture I will discuss the relation between automorphic forms on U3 and certain algebraic varieties called Picard modular surfaces. And I'll discuss that tomorrow. So these are surfaces, these are algebraic surfaces associated to the group U3. Here there is a book that's just appeared, a collection of lectures. Which I had the, some sense fortune, but in some sense also misfortune to be the editor. One learns something about human nature when one is the editor of a series like that. All right. Now, to return to U3, so that's for tomorrow. To return to U3, what are the advantages? First of all, the advantages are that the local information is available. In particular, endoscopy is understood, fundamental lemmas are available, and as I say, they're serious. And the second part, and it's a little bit more technical, but I want to mention it to you because it's used. The second part is that ultimately, somehow within the theory, say in Rogovsky's book, you use multiplicity 1 for GL3. So you use multiplicity 1. And what I want to observe is, for anyone who's really interested in the subject, is that this is something really disagreeable. And when people begin to carry out the Arthur's program, and seriously, namely when they have the fundamental lemma in general, they're going to discover that this is an obstacle to treating the general case. So probably if someone is interested in p-adic groups, he should look at the way in which the multiplicity 1 is used in, say, base change or in the treatment of U3, and see if they can understand results on the local theory well enough to avoid use of multiplicity 1. The results of Bushnell and Kutzko, for example, might be useful local results. And they're certainly not clear. All right, so let's now see what we can do for U3. So, I mean, U3 is a group, of course, over a field F. I usually take F to be global, but sometimes it will be local, and it's defined by means of a quadratic extension E over F. Now, what's the L group? So this is the group G. You may say, what unitary group? And I say, it doesn't matter. So what's the L group? The L group is GL3C, and then I take a semi-direct product with the Galois group of some large field, some large Galois extension, even F bar, over F, but certainly K has to contain E, because I let this group act on this by means of the homomorphism to this group, and sigma, which is a non-trivial action, sends A to 1 minus 1, 1, A transpose inverse 1, minus 1, 1. So this is the outer automorphism that is involved here. Now, last time I mentioned base change, I mentioned it for GLN, but one can think of base change for any group. So what's base change here? I don't need an arbitrary base change, although one could. I want to make base change from F to E. You see, that just says the L group always maps to the Galois group of K over F. If I base change says go to E, take the inverse image of the Galois group of K over E, which is just GL3C Galois group of K over E, because Galois group of K over E is acting trivial. That's the L group of a new group, so this is an L group of a group over E now, namely GL3, but over E. So if we take this L group of this group, we look at the inverse image of the Galois group of K over E, we get the L group of another group, and base change says that whenever we have an automorphic form here, then we should have one here. So, or a representation, automorphic. That would be base change. So base change is one of the things that Rogowski must and does study. He just does it for the case of a base change from F to E, because that's enough for his purposes. Okay, now what about endoscopy in this case? Let me take S in the group G hat, which is GL3C. So let me take a semi-simple element in here, and let me look at it, I suppose, so S is semi-simple, as the letter suggests. And let me suppose that the centralizer of S projects onto Galois group of K over F. So in other words, S is such that I can always, that whenever I have an element here, I can supplement it by an element here such that the pair together centralizes S. So what would the examples be? So S is semi-simple, I might as well take it to be diagonal. And the simplest case would be that it was invariant under sigma. That would mean sigma would take S, if you think of this, would take it to gamma inverse, beta inverse, alpha inverse. So if that's going to centralize S, the interesting case would be that alpha was equal to gamma inverse and that beta was equal to beta inverse. So there are several cases. There's the case that I have alpha, so beta is plus or minus 1. Up to scalars, things don't matter here. Then I have alpha inverse. Well, if alpha is not equal to alpha inverse, then the centralizer of S, which is the thing that matters, the centralizer of S is an L group itself. The centralizer of S consists of diagonal matrices together with sigma, so something which is a product of diagonal matrix with 1 or sigma. So in this case, the centralizer of S, think about it, is an L group that of M, the group of diagonal matrices. Well, that's not true. So the maximal split Cartan subalgebra of G, subgroup. So that's M. take G to be a quasi-split group. And one knows that M plays an important role in the representation theory of G. So, for example, M controls the induced representations. Second possibility for S would be 1. A second would be for S to be, say, the identity, and then this centralizer would be G itself. And a third possibility would be to take S to be, for example, 1 minus 1, 1. And then if you look at it for a bit, you see the centralizer of S consists of things of the form A, B, C, D. So the centralizer of S, first of all, has things of the form A, B, C, D, and then E with zeros here. But also it has 1 sigma. And if you think about this a little bit, you see this is basically the L group of the group H, which is U1 for here, cross U2. And U2 is, for all practical purposes, SL2 or GL2. So in the study of G, there are 2 groups that are important: this endoscopic group and this group M that one knows about, as well as the group G itself. We'll see what role these so-called endoscopic groups play later. Now, what are we trying to do? We want to understand, whatever this means. So locally, so the representation theory locally of G of F for F, a local field, and 2, the automorphic forms on G of AF for F global. So we want to understand. In what sense? By the way, I observe here, the situation here is that H sub L I can think of as a subgroup of GL. All right, so globally, let's think of things. Let's look at the global situation first, since the global situation is what we talked about last time. See, what did we say last time? We said last time we would like, and we can't do it yet, to do base change for automorphic forms, base change, and we'd like to do external products. Now, what that means, if you think about it, is the following. It means that automorphic forms on GLN AF behave as if they were the set of representations of degree n of, say, of a group, let's say locally compact group LF. Namely, this L sub F would have a map to the Galois group of F bar over F. Would have a map to the Galois group of F bar over F, because then base change would just correspond to restricting the representation to L sub E, which would be equal to the inverse image of Galois F bar over E. Well, I'm sorry, L sub K for any K Galois F bar over K if K were a finite extension. So the fact that there is a base change would mean that we could define L sub K in terms of L of F, so that means that L of F would have to map onto that. And this fact that they're external products is the thing that says they behave like representations. Because we can take the tensor product of two representations. Now, whatever was clear from the talk last time, you must have convinced yourself that I didn't know how to prove the existence of LF. So what we want to do is we want to classify the representations in terms of LF. I mean, we want to have the same classification as you would have if L of F existed without having LF. So automorphic forms on GLN behave as if they were the set of representations of degree n of a locally compact group LF, and more precisely, cuspidal, and I'm not going to define this. If you know what it is, fine. If you don't know what it is, I can maybe explain to you later. Cuspidal, let's work with representations on GLN of AF behave as if they were the set of irreducible representations of degree n of a locally compact group LF. We don't know that L of F exists, but we're going to try to find a substitute. All right. So before we work with this group LF that we don't know exists, let me introduce a second group closely related to it that Arthur introduced. So Arthur introduced the group which we'll call A sub F, which is a direct product of the group SU2 with LF. So what A sub F, so L sub F parameterizes all automorphic representations. A sub F parameterizes those that occur, say, that are actually are needed for the harmonic analysis. So L2 of GF over G of AF. That's the idea for A of F, and we're going to work with A of F. So here we'd call the parameter then is a phi which takes L of F into, well, okay, let me not worry about that for the moment. So we don't know that L of F exists, we don't know that A of F exists, and nonetheless we would like to say the following. We would like to say the automorphic representations of an arbitrary group G are classified by homomorphisms phi from L of F into GL, which are compatible with the mappings of both groups onto the Galois group. So this is a commutative diagram. We'd like to say, this is for any group, G in particular for U3. So to speak, the L2, let me put it that way, automorphic representations of G are parameterized by C, which takes AF into GL, and which compatible with the map onto the Galois group of K over F, any large K. And also the image of C should be relatively compact. Don't worry about that. I mean, what this means is we're really interested in unitary representations or unitary characters, and for unitary characters have bounded image. That's what that means. Now, these are meaningless statements, and we have to try to attach some meaning to them in the context of the group U3. We have to see what they mean. All right. So globally, this L sub f doesn't have any meaning. So therefore, neither does A sub f. What about locally? See, locally, we want to classify say, irreducible representations of G of F, say, for any group G, by maps of LF into GL. Now here, locally, we have a slightly different situation. If F equals C, then L sub F is equal to C cross. 2, if F equals R, then we have an extension of the following form. L sub F contains C cross, which is embedded into it, maps to the Galois group of C over R, which consists of two elements, 1 and sigma, and sigma lifts up to W of sigma, and W sigma squared is equal to -1, and W sigma operates on an element here, it's a normal subgroup, by conjugating it. So locally, at least over F, over C and R, we do have this L of F, and 3, if F were p-adic, then L sub F equal SU2 cross what is called the Weil group. Now the Weil group is basically a discrete subgroup of the Galois group, so let's not worry about it. The difference between the complex case and the real case, and on the one hand the p-adic case on the other, is that even locally, although we have L of F, we don't know that it does everything we want it to do. To some extent we know these things, but we don't know that it does it for every group. We know that it does it for the U3. That's one of the things that's in Rogowski's book. That for U3, L sub F does classify the irreducible representations of GF. By the way, these homomorphisms are only defined up to conjugacy by alpha in the G hat, which is the connected component. So a connected component of 1. So it's the GL3C for the unitary group. And that means we don't distinguish between phi and alpha inverse, if alpha is in G hat. Now, and this, by the way, is a different SU2. And what we do is, in these three cases, 1 and 2 in general, and 3 so far as we can handle it, we associate to phi, pi sub phi, which is called an L packet. And the situation is that the set of all irreducible representations locally of this field is the direct disjoint union of these objects. They're called L packets. Now, A packets correspond to C, which takes AF is equal to SU2 cross LF into GL. And locally, these A packets are not so nice. So these A packets, insofar as we know they exist, and we know they exist for U3. So C has the image of C is relatively compact. And the idea about C is the following. This condition means that we're not classifying so many things here as we are here. We're excluding a lot of things. And what we're excluding, if I may say it, are the representations that do not appear to be of global interest, that are excluded presumably by whatever form of the Ramanujan conjecture is true. And the fact that we have this SU2 here means that locally there's a certain amount of redundancy. It means that locally I can describe that two different A packets may contain elements in common. I'll come back to it later. This SU2, I mean, this redundancy is disagreeable, and in some respects these things are disagreeable locally, but the SU2 is also, however, useful even locally, because as I'll explain later, the SU2 is related to the SU2 of Hodge that appears in Hodge theory. So that corresponds, that is defined in terms of multiplication by fundamental classes. I'll come back to that later in the context of these Picard modular surfaces. Now globally, however, we'll see this, globally there is no redundancy, so far as we know, in the classification by A packets. And we'll see how this works for the unitary group. And what we classify are the representations we need for the harmonic analysis. And therefore, in particular, the representations we need for studying cohomology of Schmor varieties. Let's just see how this works. Let's see the role of this, of Arthur's classification, Arthur's potential classification. So let's call it Arthur's conjecture. But let's see how it works in particular cases. Let's see how it works, say, for the group GL2. Globally, because it's more interesting globally than locally. Okay, GL2, we understand automorphic forms on GL2, and let's look at AF. So AF is SU2 cross LF, and the L group of GL2 is GL2C cross the Galois group. But the mapping onto the Galois group is always prescribed. It's just that of LF onto the Galois group. So to speak of C for GL2 or for GLN in general is just to say we have a representation of SU2 cross LF in GL2. Well, you can see there are two possibilities. C could be restricted to SU2, could be trivial, or C restricted to SU2, since on the other side we have GL2C, is standard representation. So let's look at the 1 and 2. How much freedom then? If C restricted to SU2 is the standard representation, then C on L sub F has to be a scalar matrix, so alpha L. So L goes into alpha L, 0. So it's a one-dimensional representation of L. Now we don't know what L is. Now, although we don't know what L is, we know what its one-dimensional representations are. They're automorphic forms on GL1. So alpha is an automorphic form on GL1. That is, alpha is a character of the multiplicative group of the Adels, which is trivial on F cross, and therefore alpha defines an automorphic representation of GL2, namely A, B, C, D goes into, if you like, alpha is a character, so to distinguish slightly chi sub alpha of AD minus BC. So in verifying Arthur's conjecture for GL2, say in this case, we don't have to really know about L of F, we just have to know what the one-dimensional representations are. Now, psi restricted to SU2 is trivial. This is the second possibility. That means that C is basically a representation of L sub f. C is a representation of L sub f, relatively compact image, either irreducible, but an irreducible representation of LF corresponds to a cuspidal automorphic representation so this is something redundant. Arthur's conjecture, provided we don't know what L of F is, and even if we knew what it is a redundant statement. Or the direct sum, or C, takes L into alpha of L, beta L. We have two one-dimensional representations of L, and we given up to the order, and we know that two one-dimensional representations, and they're unitary. Alpha and beta are unitary. Alpha and beta, because a one-dimensional representation of L, especially that with compact image, are associated to two unitary characters, key sub alpha and key sub beta. That's just a redundant statement about L. That's what one-dimensional representations are by definition. And to these two things, we use Eisenstein series to build an automorphic form. So you see, Arthur's conjecture for GL2 just tells us, is clear. We have just enough representations to fill up all of L2. We have the cuspidal representations that fill up part. We have the Eisenstein series that fill up another part, and we have the one-dimensional representations that fill up the rest. And so that is how Arthur's conjecture looks for GL2. It's been proven for GLN in this same form by it's been proven by Meglin and Walsberger. If you look at, I think there's an exposition of this in Meglin Kyoto talk. In that form it was conjectured also by Jacquet. All right. You can work. You can think about it, what it means for GL3. Let's now, however, go to U3. For GLN, by the way, in contrast to other groups, L packets only have single elements. Now, so let's think of U3. So you now have C, which takes AF into GL, which you remember is for U3 is GL3 C cross the Galois group of K over F. You notice we're doing representation theory without ever introducing representations. So I can restrict C to this SU2. So there are three possibilities. A, this restriction is trivial. B, it's a direct sum of a one-dimensional representation plus a two-dimensional. In other words, as I said, this is when I pass to the Galois, I mean, as far as C on AF on the SU2 part, this is equal to SU2 cross a hypothetical LF, and the SU2 part has trivial projection on the Galois group. So as far as C restricted SU2 is concerned, we're dealing with a three-dimensional representation. Or C, it's irreducible. All right. So let's look at C takes a G cross L into general C of G, which is the three-dimensional representation, cross say, okay, C of L cross sigma of L. So this is the image of L in the Galois group. And in particular, as we pointed out, we can restrict C to L of E. And C restricted to L of E is C of E sub E of G, which doesn't change, cross CE of L. And now we have a direct product here, so we can just forget the last part. So restricted to L of E is the quadratic extension. We have a three-dimensional representation of L. So you see, we said this before, what is this? You see, C restricted to LE is basically a map into GL3C, and we know, as I said, because Arthur's conjecture in the form we want it is valid for GL3, we know that these things correspond to something. I mean, whenever we have one of these, even though we don't know what L is, we have something. We have an automorphic representation. It really labels an automorphic representation. This is just some symbolic way. So the Arthur's conjecture certainly wouldn't be possible without at least the base change to this quadratic extension. Let's look at it a little bit carefully. Let's look at the case C, where C restricted to SU2 is irreducible. In this irreducible three-dimensional representation of SU2, then C sub E just takes L into alpha of L, alpha of L, alpha of L. So this alpha it really is a one-dimensional character chi sub alpha of GL1, but for the del's over E, which is equal to AE cross, it's trivial on E cross. I mean, that's what a one-dimensional representation of E is. Now, what does that mean? So suppose I take an element. Now suppose I take G. If I take G in G, or let me call it A in G sub AF, then the determinant of A is equal to, is an element of U1. AF. It's an, all right, that's what the determinant of A, let's call it X. Now you see what I want to do. What I want to do, trying to verify Arthur's conjecture here, I have to associate to this C some representation of G, automorphic representation of G. And you can guess what I want to do. Since C restricted SU2 is irreducible, I have, so to speak, a one-dimensional representation floating around from the definition of LE at least, and I want to get from that representation this chi sub alpha to a character of X. Now X is in U1AF. That means X bar is equal to 1. X is not in AE. But X is equal to, then, by Hilbert's theorem 90, X is equal to the quotient of Z by Z bar. This is theorem 90. So I would like to say, okay, write X as Z over Z bar, and I'm going to say, let's define pi of A to be a character evaluated at X, but what character? I don't have a character defined on this group, I have a character defined on this group, so it has to be something evaluated at C, so I could say at Z, I could say chi sub alpha of Z. But then, in order for this to make sense, need chi sub alpha of AZ equal to chi sub alpha of Z for any A in A sub F. So for an del in F, I need chi, so it is chi sub alpha of A is equal to 1. Otherwise, the value on the right-hand side would depend on the choice of Z, and that's not allowed. Well, what is it that's forcing this condition? I go back here and I said, well, so far I've only worked with CE. I've only worked with this restriction, the restriction to the L group, to the group over E. The condition that this CE, so CE extends from LE to LF, which is what I need. When I look at see what that condition means, it just amounts to this fact. All right, so I mean, working with, I still don't have LF, but I can work as though I had it. All right, so I have verified Arthur's conjecture in this third case. All right, so let's now go to the first case, and let's suppose that C sub E trivial on SU2. So that means there are several possibilities. That means that C sub E is just an arbitrary representation of LE. This is C restricted to AE, by the way, because I have the two. So C is an arbitrary, for all practical purposes, so this is an arbitrary representation of LE, three-dimensional, but a compact, relatively compact image, don't worry about that. So there are several possibilities. C to be irreducible, and these are just the cusp forms. All right. So these are just the cusp forms. Now, so what I have then, I mean, that's the definition of LE. That is, over here, I really know by the very definition of LE that a CE irreducible corresponds to a cusp form for GL3E, but GL3E over GL3AE. So this is a representation of GL3AE. This is a long way, or it appears to be, a long way from a representation of G of AE. They're two different groups. All right. Now, what would it mean? What does it mean to say formally? What does it mean to say that this extends? This extends to C. This is a formal condition, and this is a condition I impose. What can I understand what that means? What that means on the other side? Yes, it's easy enough to see what it means on the other side formally. Is that pi sub E applied to a scalar matrix is equal to the identity. So it means the central character of pi sub E is 1. This formal condition is equivalent to this condition, and what Rogowski proves is, Rogowski proves that his base change provides a bijection between automorphic cuspidal representations of GL3 AE satisfying star, so this is star, and a collection of, say, of packets of representations of G of AF. I'll explain what a packet is, but the point is that each time I have a representation of this type, I have a collection of representations of G of AF, and these collections are disjoint. And it's natural to say, well, this must be pi of C. In the special case that C sub B is irreducible. I still have to deal with the other cases, of course. And by the way, it's even there are two possibilities here. If C of E is reducible, it may be reducible and admit deformations, or it may be reducible and because of this condition admit no deformations. It will depend. So we're not finished yet. I don't know to what extent I just want to say, I don't want to say too much. Let me say a little, however, about what happens in other cases. All right. So what we have to discuss is the case with C restricted to SU2 is trivial. So, but C sub E, so now is a representation of LE is not irreducible, is reducible. What this means is one of two things. I don't think I want to go into detail, it becomes rather complicated, but it really means one of two things. It really means that C factors through M This was one of the first endoscopic groups that I put up. That means that the representations associated with C are Eisenstein series, so we're working with the continuous spectrum, or it means C factors through HL goes into GL, and that means that basically, if you think about it, somehow C sub B is described in terms of automorphic representations on GL2AE and GL1AE. It all works out in any case. I mean, you can. Here, this is basically the case that there's some deformation is possible. This is basically the case, apart from overlap, where no deformation is possible. So these are representations that occur discretely in general, and these do not. But you work it through, and you see that indeed Arthur's conjecture is true. By the way, there is something peculiar here. In the book there's a mistake. In the book of Rogowski there's a mistake, and there's the mistake, I won't go into it, the mistake is there because he assumed that his results, Arthur's conjecture, must be true, confirmed Arthur's conjecture. Arthur repeated this in a paper of his, but in fact Rogowski's results in the first version did not confirm Arthur's conjecture, and they were false. I mean, when they're corrected, they confirm it. It's rather, Arthur's conjecture, I haven't gone into detail, involves some subtle constants, and they weren't right in Rogowski's first paper. But in the second book I mentioned on Picard surfaces, I they're supposed to be corrected. It was caught by Harder. The error was caught by Harder on altogether different grounds. All right. Now, one question we haven't really discussed, you see, we haven't discussed the fact that, and I just want to mention something about this, that pi sub c does not always consist of a single element. Basically, locally, if c factors through h, L, then pi sub c consists of 2, sometimes 4 elements. This is just a fact of life. This is true, and one just that's what endoscopy is all about, the study of that situation. Now, another thing that should happen is L sub f should contain the corresponding local form. This is just this is something you know from Galois theory, that Galois groups contain the local form, and this just corresponds to the fact that an automorphic representation is a tensor product over all places of irreducible representations of the corresponding local group. Now, how does this set pi sub psi look? Pi sub psi will be a collection of pi, and they'll all be tensor products, and pi sub v will belong to the corresponding local thing. Now, as I said, this local thing will usually have, sometimes it will consist of a single thing, but if that local element, even if this global homomorphism does not factor through H, the local thing may. So the local thing may have 2 or 4 elements. In fact, it will often be the case. So it's indeterminate. That means that there are a lot of pi's in this set, because I may be able to change them locally one at a time, but they're an infinite, since this locally the set is, there are more than one possibility for pi v. I can modify pi v, even if I only modify it at a finite number of places, in an infinite number of ways. So this is generally globally infinite. But in addition, arbitrary modifications are not allowed. There are constraints in the nature of product formulas on these pi v's that I don't want to go into. They're built into the conjecture, and one understands them to some extent. I'll discuss their consequences next time. Let's just understand they exist. All right. And so that's the reason that this set is so large because locally it's often large. All right. Now I just have one more remark to make before stopping. Something we'll come back to next time. But let's look at the particular case. We didn't do it yet. It's the same situation, that C restricted to SU2 is one-dimensional plus two-dimensional. That means that it takes its image on matrices of this form. Well, it'd be 1, CD. So that's the A in SU2. An element of SU2 would go to this. And that means that on L, after all L commutes, that C on L is equal to, let's say, C sub E, of the form alpha of L, beta of L, alpha of L. That means that as far as the L part is concerned, all the information is really contained is abelian. So information is abelian, because all we have at our disposal are 2 characters of L. So this is a part of the Arthur classification. The Arthur classification says there is a special type of representation corresponding to those C whose restriction to SU2 is one-dimensional plus two-dimensional, and for these the information contained in the L part is abelian. If you translate that information into geometric language, what it will say, and we'll see this next time, is it says that the Albanese variety of a Picard modular surface is of CM type. So this is proved in these notes on Picard modular surfaces that I mentioned by Kumar-Murthy and Ramakrishnan. So it still has to be proved, but it can be regarded as a consequence of this aspect of Arthur's conjecture. I'll come back to it next time. But anyhow, that's all I wanted to say for today. I think my time, in case went up. I don't know whether I should ask for questions or...